Good morning, friends and students. We are going to discuss about supramolecular chemistry. So, what is supramolecular chemistry? That is main important point to us. All of us know about the molecules. So, if we go to formation of a molecules, it contains some covalent bonds. Again, if we go for a chemical reaction, there also two molecules try to combine themselves by a covalent bond to generate a new molecule. So in all cases, always we are dealing with molecule, and these molecules also try to bind themselves in a covalent bond. Now, beside the molecule formation or the dealing with combination of two molecule by a covalent bond, we may find out interaction between two molecules. That is, if two molecules come closer and they try to attract or repulse themselves, not by forming any covalent bond, they may also aggregate or combine themselves by utilizing some another interactions, that is called non-covalent interactions. So there also we may find out actually interaction between two molecules without involving covalent bond, that is only the weak interactions. So the chemistry, the supramolecular chemistry deals with that kind of interaction. According to the scientist Geomary Lane, who received the Nobel Prize in the supramolecular chemistry area in 1987, he suggests that supramolecular chemistry is nothing but the chemistry beyond the molecules. So here we considered the non-covalent interactions, that is, we also considered what kind of interaction present into the molecular assembly where we are not forming a new molecule. Okay, so now if we try to find out the points in which practical field we can apply this supramolecular chemistry, or what kind of chemistry actually falls into the umbrella of the supramolecular chemistry. So here you may find out the points. Their practical diversity, it contains molecular devices and machines, molecular recognition, organometallic chemistry. Organometallic chemistry means it is also actually the coordination sites, the ligands that bounds to the metal, that is all over the organometallic chemistry or coordination chemistry falls under the umbrella of the supramolecular chemistry. Another cell processes means that is the formation of micelle. If you go for surfactant, when we add some surfactant to the water, it will form some micelle. So micelle means there is actually a self-assembly formation. That also falls under supramolecular chemistry. Another dynamic covalent chemistry and also interface, nanochemistry, everything comes under the supramolecular chemistry. Next, what is the difference between molecular chemistry and supramolecular chemistry? When we try to find the molecular chemistry, here I already said that there some covalent bond will form when two different molecules or three different molecules, they try to react together to generate a new molecule. So if you generate a new molecule, then we have to purify the molecule, then we have to analyze the molecule, whatever the chemical structure that deals with the new molecules, also their homo-lumo gap, their redox property, their shape, their X-ray crystallographic structure, etc., etc. So in case of supramolecular chemistry, there also a formation of new molecular assembly. That is, we may see here there is a guest molecule and there is a so there is a guest molecule and there is a host molecule. This guest molecule and host molecule, they try to combine to generate a new molecular assembly. This molecular assembly, there is no covalent interaction. Just see there, in this structure there is no covalent structure, covalent bond has been formed between this host and guest. So if you just tune the external parameter, that is any pH, temperature, solvent, whatever it is, these two molecules, host guest, can be actually formed there previous structure directly. That is, if we change the pH, the guest molecule may come out from the cavity of the host, and we will get just two distinct nature of these two host and guest molecules. So there is just the combination of host and guest molecule by weak interactions. After forming this type of supramolecular complex, we have to analyze the property of the complex, and also we have to recognize the complex by measuring their degrees of order, interactions between the subunits, summary of packing, and intermolecular interactions. Okay. So what are the applications of this kind of molecular assembly? We can apply this molecular assembly for as catalyst. We can analyze this system as molecular machine to generate energy. We will discuss in future or in our later slides also about that. That is molecular devices. Also we can use this system as actually a photochemical catalysis and photochemical devices, dendrimer, etc. etc. Okay. Next, why any people, that is any scientist, they think about the supramolecular chemistry? Why they try to analyze this? What is the necessity? Actually, the inspiration comes from the biological system, that is in our body, in any microbes, in bacteria, virus, whatever, how they are working. Are they changes always in our body by making some covalent bond? No. Or if we try to find out any kind of system, any process, what happened in our body, that is suppose a respiration, reproduction, if we try to respond any external stimuli, that is if we face some mosquito bite in our surface, in our actually skin, then automatically our hand try to react something, try to react over them. So this type of control of external stimuli, that is not dealing with any formation of a compound. It takes much time, it takes much energy to form a covalent bond, but it reacts by only using host-guest chemistry. Now here you can see this is a hemoglobin structure, that is heme unit, right? So in this heme unit there is an iron molecule present. So when we actually try to inhale oxygen, what happened? The oxygen molecule go to bind to this heme unit, that is the iron, and then after going to the cell it will release the oxygen. So there the formation of a non-covalent or coordination bond of this oxygen to the heme unit or this iron occur. Again this bond actually, when the release of oxygen occur, then the bond breaking occurs, and this bond making and breaking does not contains high amount of energy like covalent bond, so it is a easy process and it happens in our body. So as in our body or any kind of biological processes involves the formation and disruption of non-covalent bond. So the chemistry behind this kind of interaction has some importance, right? So to analyze this importance, this chemistry, every person or this scientist, Geomery Lane, they try to find out the chemistry behind covalent molecules, that is supramolecular chemistry. Okay, next we can go for the journey of finding out or discovery of the molecule from inorganic to organic compound and organic to supramolecular compounds. Students, you can say that if we try to find out the first synthesized organic molecule, that is nothing but the urea. Urea is the first synthesized organic molecules. It comes from ammonium cyanide. Ammonium cyanide is an inorganic molecule. Inorganic molecule ammonium cyanide try to break up into ammonia and hydrocyanic acid, and after that their combination will generate a urea. So urea is the first organic molecule. And again, if we try to find out after a long journey, this is actually synthesized in 1828, and after a long journey near about 100 years, there in 1972, vitamin B12 has been synthesized as the most complex unit till now. So this is a supramolecular compound. Supramolecule means it is a big molecule, and there is a molecular assembly, already I have said, including actually some non-covalent interactions. Here the actually cobalt molecule, cobalt ion is present there into the center of this chlorine or porphyrin type of ring. So here some covalent, non-covalent, actually coordinate bond is present, right? So this is a supramolecule or a macromolecule also. So this vitamin B12 is the most complex molecule, has been synthesized till date. Okay, so here we can see, or we can find out the journey from inorganic to organic to supramolecular compounds. Okay, so next, if we try to find out the importance of this field till now, what is the importance? So if it is actually an important phase or important aspects of science, so there should be some impact on the society, and if it has some impact on the society, so there the work can be recognized by getting a Nobel Prize. So if we try to find out the Nobel Prize in this supramolecular chemistry field in a previous date, that is in 1987, Donald J. Cram, Geomedi Lane and Charles J. Peterson, they get the Nobel Prize. They get the Nobel Prize for their development. Here it is for their development of and use of molecules with structure specific interaction of high selectivity. What does it mean? Structure specific interaction. There this interaction is non-covalent interaction, obviously, because we are dealing with supramolecular chemistry. So if we try to find out what is this structure specific interaction, let's see. So here, if we try to find out the interaction between a drug and a receptor, so always when we take a drug, just a minute, yeah, leave it, I try to write down again, there will be a problem. Here is it. So here, if we go for this system, now if it is a receptor, now you have a drug with this symmetry, with this kind of symmetry, and with this kind of symmetry. Between these three drugs, can you suggest which drug will be fitted perfectly into this receptor? Now this drug has a square or rectangular type of shape, whereas if we go for this is a triangle, this is a actually sphere. So now according to this receptor structure, it has an opening only for accepting a square or rectangular type of system. So this actually specific bindingness, or that is interaction specificity, will be discussed or discovered by that three scientists. Okay, so there if we try to find out, this is actually structure specific interactions occur. So Peterson, Lane and Cram laid the foundation of what is today one of the most active expanding field of chemical research, a field for which Cram has coined the term the host case chemistry, while Lane called it as a supramolecular chemistry. Okay. Next, again, if we find out a recent Nobel Prize, that is in 2016, Sauvage, Stoddard and Ben Feringa, you know that about, right? So they got the Nobel Prize in making molecular machines. Molecular machines means today in our life we deals with multiple machines, that is we are using fan, AC for actually comfortable and for making comfortable environment, etc. So they consumes a large amount of energy, so there will be some energy resource in a molecular level. So they try to make some molecular machines in molecular level. That is, if we go to find out some molecular machine, like if there is a molecule where there is two binding center 1 and 2, suppose here a binding center which can bind to a circle, and by changing just only external stimuli like pH, this cycle can continuously go up and down from this point to this point. So as this system, this circle is going up and down continuously, it deals with some energy. So this is also like a machine. There is a continuous movement of something, right? So it should generate some energy. So we may find out, or we may synthesize some molecule like this, and in this molecule, this cycle, this is a actually rotaxane, in which this is axle and this is a rotator. So there, this molecule continuously, it has a binding with this center in a supramolecular fashion or weak interaction fashion. So continuously they are moving up and down, that is making actually a molecular machine. So here also actually an important discovery of molecular machine by these three scientists, and for that thing they are getting the Nobel Prize. Okay student, we are not discussing many things now. So actually in further class we will discuss about that. Thank you for your kind listening and interest. Okay, thank you.